Imagine your phone, like, perfectly filtering out all that background noise when you're on a call. Or maybe your car stereo, delivering really crystal clear audio, even when you're driving on a bumpy road. These things, they aren't magic tricks. They're actually the silent work of this technology that underpins, well, almost every piece of modern electronics we use. Today, we're doing a deep dive into the fascinating world of digital filters. Our listener, you, shared some really incredible sources with us: academic slides, detailed university lectures, all sorts of things to help understand what these are, how they work, and why they're just so crucial. So our mission today is to unpack all that material and give you a kind of shortcut to being well-informed, hopefully with plenty of aha moments along the way.
Yeah, and at their core, digital filters are essentially sophisticated algorithms, really. They take a sequence of numbers that's your signal, represented digitally, and they meticulously transform it.
Mm.
The goal is to produce a desired output, whether that's, suppressing noise, enhancing specific frequencies, or maybe completely reshaping the signal.
Okay, let's unpack that a bit more then. What exactly is a digital filter?
Yeah.
And how is it different from, say, an analog filter, the kind many of us might picture with, like, actual physical components on a circuit board?
Right. At its most basic, a digital filter is a numerical procedure, an algorithm. It takes an input sequence of numbers, okay, and it converts it into an output sequence that has, well, more desirable properties.
Mm.
And this all happens inside a digital processor. That could be anything from a general-purpose computer to a specialized chip, the DSP, digital signal processor. The fundamental distinction from an analog filter is really key here. Analog filters operate on continuous electrical signals. They use physical components, resistors, capacitors, inductors, stuff you can hold. A digital filter, on the other hand, manipulates sampled discrete values of that signal, numbers.
Ah, okay, discrete values.
Exactly. Once it's inside the processor, the signal exists purely as a sequence of numbers.
And your sources included a really great block diagram showing this whole journey. It starts with an unfiltered analog signal, then goes through an analog to digital converter, an ADC, then into a processor, and then after the filtering happens in the processor, it passes through a digital to analog converter, a DEC, to become a filtered analog signal again. Could you walk us through that transformation? What's happening at each step?
Absolutely. So you start with your analog input signal, right? A continuous voltage like a sound wave. First, it hits the ADC. The ADC samples, takes rapid snapshots, and digitizes it, turning those continuous voltages into a sequence of binary numbers.
Okay, so it's slicing it up into number.
Precisely. Then these numbers are fed into the processor. The processor performs mathematical calculations on them, mostly multiplying these number values by certain constants, we call these coefficients, and then adding the results together. If the final output needs to be analog again, maybe to drive a speaker, these process numbers are converted back by the DAC.
I see.
But the really critical insight, the key thing, is that within that processor, the signal is just a sequence of numbers being manipulated mathematically.
Right, right. So if there's all this conversion going on, analog to digital, then digital back to analog, it makes you wonder, why not just stick with analog filters? What makes digital filters so much more, I don't know, powerful or practical that we go through all that effort?
That's a really good question. And there are reasons to use analog sometimes. But digital offers some compelling advantages, which your sources really highlight. First off, programmability. A digital filter's operation is defined by software, by code. This means you can easily change how the filter behaves just by changing the code. No need to touch the hardware.
Ah, okay. So you just update the software.
Exactly. With an analog filter, if you want to change its characteristics, you often have to redesign the physical circuit. Solder new components, it's much less flexible. Second, there's exceptional stability and reproducibility. Think about analog components. Their values can drift with temperature, they have manufacturing tolerances, they age.
Right, like an old guitar amp sounding different depending on the weather.
Exactly. Digital filters don't have that problem. The coefficients, the numbers defining the filter, are stored precisely in memory. This makes them incredibly stable, predictable. Doesn't matter if it's hot or cold, or if it's this chip or that chip, they behave identically. This allows for really complex, high-order designs that would be almost impossible to make reliably with analog parts. Third, versatility. They're great at handling very low-frequency signals accurately, which can be tricky for analog. And they're increasingly being used for high-frequency stuff too, like in radio communications. Plus, some digital filters are adaptive.
Adaptive, what does that mean?
It means they can actually change their own characteristics in real time based on the input signal, like noise cancellation that adjusts to the specific noise around you.
Wow. Okay.
And finally, they're often easier to design, test, and implement using computers. You can simulate everything before you build anything. And modern DSPs can handle lots of complex filters together, often making the overall hardware simpler than a comparable analog setup.
Okay, that's a pretty convincing list of advantages. Programmable, stable, versatile. But, engineering is always about trade-offs. There must be some downsides, right?
Oh, absolutely. There are trade-offs. For one, digital filters can be more expensive, especially for simpler tasks, because you need the ADCs, the DACs, the processor.
Mm.
That's more complex hardware than a few resistors and capacitors.
Right, the overhead.
Exactly. And they introduce latency, a time delay. This comes from the time it takes for the conversions, the ADC and DTA, and also the time the processor needs to do the calculations. For real-time audio, like live music processing, that delay can be a problem.
Ah, okay. I can see that.
Also, digital systems deal with discrete numbers, so there are unavoidable errors related to rounding those numbers, called quantization errors. Analog filters don't have that specific issue because they work continuously. So for very simple fixed tasks, or where minimal power consumption is absolutely critical, analog might still be the better, more efficient choice.
Got it. So we know why they're powerful. We know the trade-offs. Now, how are they actually constructed? If it's all algorithms and numbers, what are the fundamental building blocks?
It's actually built from surprisingly simple operations. There are really only three fundamental building blocks for all linear digital filters. First, adders. Simple enough, they just sum two or more signals or number streams together.
Okay.
By 1n plus by 2n, that kind of thing.
Okay, just addition.
Second, multipliers. These scale a signal by a constant value. We talked about those filter coefficients earlier.
Yeah, the numbers that define the filter.
Right. The multipliers apply those coefficients. So like LES, these coefficients are the key. Their specific values determine exactly what the filter does. And third, delays. This is maybe the most interesting one. It's often represented by Z1 in the math. A delay element basically holds the current input value for one sample interval, one tick of the clock. Then on the next tick, it outputs that previous value is holding. So xn1.
So it's like a one-step memory.
Exactly. And you can chain these delays, Z2, Z3, so the filter can access not just the last sample, but the one before that and the one before that and so on. This memory is crucial for creating complex filter responses.
Wow. Just adding, multiplying, and delaying. It sounds almost too simple, but I guess the complexity comes from how you combine them. You shared some examples of how these create actual filters. Can you tell us about something simple, like a pure delay filter or that three-sample averager you mentioned?
Sure. A pure delay filter is about the simplest you can get. Its equation is just yn, xn1. All it does is take the input signal, xn, and output the value from one sample time ago, xn1. It uses just one delay element. We'd call that a first-order filter because it depends on one previous value.
Okay, it just shifts the signal in time slightly.
Exactly. Then you have something like a three-sample averager. Its equation might be yn plus xn1 plus xn2, 3. So it takes the current input xn, adds it to the previous input xn1 using one delay, and the input before that xn2 using two delays, and then divides by 3 to get the average.
Right, averaging them out.
And what that averaging does, effectively, is smooth out rapid changes. High-frequency noise gets averaged away. So it acts as a simple low-pass filter. And because it uses the two previous inputs, xn1 and xn2, it's a second-order filter.
So the order tells you how far back in time the filter looks.
Pretty much. The order of a digital filter is formally defined as the largest number of previous input or output values needed to compute the current output. It's a measure of its complexity and its memory, essentially.
Okay, that makes sense. Now, digging a bit deeper, your sources really emphasize two main types or architectures for digital filters, FIR and IIR. What's the fundamental difference there, and why would an engineer pick one over the other?
Yeah, that FIR versus IIR distinction is really fundamental. It boils down to how they use past information, specifically whether they use feedback. FIR stands for finite impulse response. These filters are fundamentally non-recursive. That means their output is calculated only from the current input and a finite number of previous inputs, xn, xn1, xn2, etc. Crucially, they do not use feedback from past output values, in1.
Okay, so they only look at what's coming in.
Right, and the name finite impulse response means if you feed in a single brief pulse, an impulse, the filter's output will react, maybe wiggle around for a bit, but then it will settle back to zero after a finite number of steps. Its response dies out. IIR stands for infinite impulse response. These filters are recursive. Their output depends on current and previous inputs, and critically also on previous output values, in1, in2, etc. There's a feedback loop.
Ah, so they look at what they just did as well as what's coming in.
Exactly. This feedback means that, theoretically, if you hit it with an impulse, the output could keep ringing or decaying forever, hence infinite impulse response.
Hmm.
In practice, it usually decays to effectively zero, but the potential for infinite response is there. And because they use past outputs, IRR filters, by definition, have to be at least first order. They need that feedback path.
Okay, so FIR is input only, IRR uses feedback. What are the big advantages of FIR filters then? Why choose them?
The killer feature, the real game changer for FIR filters, is that they can be designed to have perfectly linear phase response.
Right, you mentioned this earlier. All frequencies get delayed by the same amount.
Exactly the same amount. This means the filter doesn't distort the shape of the waveform in time. All the frequency components stay perfectly aligned as they pass through.
And that's vital for high-fidelity audio, medical imaging.
Precisely. Anything where preserving the exact waveform shape and timing relationships is critical. If different frequencies got delayed by different amounts, which is what happens in nonlinear phase filters, you'd get phase distortion, smearing the signal in time. FIR filters avoid that completely. They're also inherently stable because there's no feedback, they can't run away and oscillate, and they tend to be less sensitive to quantization errors.
Okay, linear phase and stability sound like huge pluses. So what about IIR filters? What's their unique selling point? Why use feedback if FIRs are so well behaved?
Efficiency, pure and simple. Computational efficiency. IIR filters can often achieve a desired frequency response, especially a very sharp cutoff between frequencies you want to keep and frequencies you want to block with a much lower filter order than an equivalent FIR filter.
Meaning fewer calculations?
Fewer calculations, fewer multiplications, fewer delay elements, less memory needed. This makes them much faster and less power hungry for the same filtering job.
Ah, so if you're resource constrained, like on a mobile device or embedded system.
IIR filters are very attractive. They give you more bang for your computational buck. They're also really good at mimicking the behavior of traditional analog filters, if that's something you need to do.
Interesting. So it's a trade-off between the perfect phase and stability of FIR versus the efficiency of IR.
Largely, yes, though both types were described mathematically by linear difference equations, and engineers analyze both using something called the Z-transform.
Okay. So regardless of whether it's FIR or IIR, the goal is usually to shape the signal in some way, like cleaning up noise or isolating frequencies. Your sources kept mentioning 4 basic types of filters based on what they do to the frequency spectrum. Can you give us a quick rundown of those?
Sure. These 4 really cover the fundamental frequency shaping tasks. First, the low-pass filter. Its job is to pass low frequencies from 0 Hz up to a certain cutoff point, let's call FP, and block, or attenuate frequencies above that point.
Like a smoother, getting rid of high-frequency hiss or sharp edges.
Exactly. Think of it as letting the slow changes through and stopping the rapid ones. Second, the high-pass filter. It's the opposite. It passes high frequencies from a cutoff frequency, say Fs, up to the maximum possible frequency in the system and blocks the low frequencies below S.
Useful for maybe removing low-end rumble or emphasizing sharp details?
Precisely. Removing DC offsets or low-frequency hum or enhancing edges in images. Third, the bandpass filter. This one passes only a specific range or band of frequencies. It blocks frequencies both below and above that desired band.
Like tuning into a specific radio station, you only want that station's frequency band.
Perfect analogy. You're isolating just the frequencies of interest. And fourth, the bandstop filter, sometimes called a notch filter. This does the opposite of bandpass. It blocks a specific range of frequencies, its stop band, and lets everything else through, both lower and higher frequencies.
Ah, so this would be good for getting rid of a specific annoying hum, like 60 hertz power line interference.
Exactly. If you know the frequency of the interference, you can design a notch filter to surgically remove just that frequency without messing up the rest of the signal too much.
That makes sense. 4 basic tools for shaping the spectrum. Now, what about this idea of ideal filters versus real-world filters? The sources mention this distinction.
Right. An ideal filter is a theoretical construct. It's the perfect version. Like an ideal low-pass filter would have a gain of exactly 1, passing everything perfectly, up to its cutoff frequency, and then instantly drop to a gain of exactly 0, blocking everything perfectly right at the cutoff. A perfect brick wall response, and it would have perfectly linear phase.
But reality isn't usually that neat, is it?
Not at all. Designing truly ideal filters is physically impossible. Real filters always have a transition band. Instead of an instant drop from pass to stop, there's a gradual slope where the filter's response rolls off. The signal is partially attenuated in this region. And the phase response isn't perfectly linear either, especially for IIR filters. So engineers design filters to get as close as possible to the ideal behavior within the constraints of complexity, cost, and allowable delay. It's an approximation game.
Okay, that makes sense. It's about getting close enough for the application. So we've covered what they are, why we use them, the basic types. Now, let's get a bit more technical. How do engineers actually characterize these filters precisely? How do they design them? And what are these things called poles and zeros that kept coming up in your sources? They sound important.
They are incredibly important. To really understand and design a filter, engineers use its transfer function, usually written as HAZ. Think of HAZ as the filter's complete mathematical DNA. It's typically expressed as a ratio of two polynomials in a complex variable z, let's say bz. This function tells you exactly how the filter will respond in terms of both magnitude gain and phase shift to any input frequency. It's the blueprint.
Okay, a mathematical blueprint. And the poles and zeros come from that.
Exactly. They are the roots of those polynomials. Zeros are the roots of the numerator polynomial, bz. These are the values of z that make the transfer function equal to 0. Geometrically, if you plot these zeros on a complex plane, the plane, frequencies close to a zero that lies on the unit circle will be heavily attenuated by the filter. The filter's magnitude response dips down near a zero. They create nulls.
So zeros make the filter block certain frequencies?
Essentially, yes. Poles, on the other hand, are the roots of the denominator polynomial, az. These are the values of z that would make the transfer function theoretically infinite. Frequencies close to a pole that's near the unit circle will be amplified or resonated by the filter. The magnitude response peaks near a pole.
So poles make the filter boost certain frequencies. It's like they define the peaks and valleys of the filter's response curve.
That's a great way to put it. The placement of these poles and zeros on the z-plane is how engineers meticulously shape the filter's frequency response to be low pass, high pass, or whatever is needed.
But you mentioned earlier that stability is crucial. How do poles and zeros relate to whether a filter is stable or, might blow up?
This is absolutely critical. The location of the poles determines stability. For a filter to be stable, meaning its output won't grow infinitely large, for a normal bounded input, all of its poles must lie strictly inside the unit circle on the z-plane.
Inside, not on or outside.
Strictly inside. If even one pole is on the unit circle, the filter is marginally stable. This might oscillate forever. If any pole is outside the unit circle, the filter is unstable. Its output will likely grow exponentially, which is usually very bad.
Wow. So pole placement isn't just about shaping the frequency response. It's fundamental to making the filter usable at all.
Absolutely. And there's another concept tied to this, causality. A filter we can actually build must be causal. That means its current output can only depend on the current input and past inputs or outputs. It can't depend on the future.
Right. You can't react to something before it happens.
Exactly. In terms of the transfer function, causality generally implies that the number of poles should be greater than or equal to the number of zeros. It's related to ensuring the filter's response doesn't start before the input arrives.
Okay, so design involves placing poles inside the unit circle for stability, placing poles and zeros strategically for the desired frequency shape, and ensuring causality. Once the math is done, H is defined. How do you actually build it? How do you turn that equation into software code or hardware logic? This is the realization part.
Correct. Filter realization is the process of translating that mathematical transfer function, ATA, into a practical structure of adders, multipliers, and delays. And interestingly, for the same transfer function, there can be many different realization structures.
Why different structures for the same filter?
They have different practical properties. Some might use fewer delay elements, saving memory. Some might be less sensitive to the precision limits of the numbers, reducing round-off errors. Some might be better suited for parallel processing. Common forms include Direct Form 1 and Direct Form 2. These are pretty straightforward implementations based directly on the filter's difference equation. Direct Form 2 is often preferred because it usually uses fewer delays. For higher-order filters, especially IR filters, it's very common to break the filter down into a series, a cascade, of simpler second-order sections, often called biquads.
Why break it down?
It significantly improves numerical stability. Implementing a high-order filter directly can lead to problems where small errors in the coefficients cause large changes in the response. Cascading biquads keeps the numbers involved in each section more manageable. And for FIR filters, especially long ones, A very efficient method called fast convolution is often used.
Fast convolution, that sounds like it uses the FFT.
Exactly. Instead of doing the multiplication and summing directly in the time domain, which gets very computationally expensive for long filters, you use the fast Fourier transform, FFT. You transform the input signal block and the filter's impulse response into the frequency domain using the FFT, do a simple multiplication there, and then use the inverse FFT to get the filtered output back in the time domain.
So you convert to frequency, multiply, convert back.
Right. For filters above a certain length, this FFT-based approach can be significantly faster than direct convolution. Techniques like overlap add or overlap save are used to handle continuous streams of input data in blocks.
Fascinating. So lots of different ways to actually implement the same mathematical idea. Now, connecting all this back, where do we encounter these filters in everyday devices, maybe without even realizing it? You mentioned ADCs and DACs earlier.
Yes, two absolutely critical filter types work right at that analog-digital boundary. They're essential guardians, really. First is the anti-aliasing filter. This is a low-pass filter, but it's placed in the analog domain before the signal even gets to the analog-to-digital converter, ADC.
Before digitization, why?
To prevent aliasing, remember the ADC samples the signal at discrete points in time. If there are frequencies in the analog signal that are higher than half the sampling rate, that's the Nyquist frequency, FS2, the sampling process itself will cause them to falsely appear as lower frequencies in the digital data.
Ah, like seeing wagon wheels spinning backwards in old movies.
Exactly that kind of effect. It creates distortion, signals that weren't really there at those lower frequencies. The anti-aliasing filter is designed to chop off those potentially problematic high frequencies before sampling, ensuring only frequencies the ADC can handle correctly actually get digitized.
So it cleans up the signal before it goes digital? Makes sense. What's the other one?
The other guardian is the reconstruction filter. This is also a low-pass filter, but it's placed in the analog domain after the digital-to-analog converter, DAC.
After conversion back to analog, why is it needed there?
When the DAC converts the digital samples back to analog, the raw output often looks like a staircase. It holds one voltage level, then instantly jumps to the next.
Right, those sharp steps.
Those sharp steps, those abrupt edges, actually contain a lot of high-frequency energy harmonics that weren't necessarily in the original signal we wanted to reconstruct. The reconstruction filter smooths out that staircase waveform, removing those high-frequency artifacts generated by the DAC process itself.
So it smooths out the jaggies, basically.
Precisely. It helps recreate a smooth, continuous analog signal that more closely resembles what was intended, getting rid of the digital artifacts from the conversion. Its cutoff is typically at or just above the Nyquist frequency.
So anti-aliasing on the way in, reconstruction on the way out, they really are essential bookends for any digital signal processing chain involving real-world analog signals. Okay, wow. We've really gone from the basics of what a digital filter is through FIR versus IIR, poles and zeros, realization, and these crucial interface filters. It feels like we've covered a huge amount of ground. You, our listener, should now have a much deeper appreciation for these silent heroes that are constantly shaping the sounds we hear, the images we see, the data our devices process every single second.
It really is a fundamental technology. And thinking about the future, it raises some interesting questions. Given the power, the flexibility, this ever-increasing efficiency of digital filters, especially with newer developments like adaptive filters that learn, or even more complex nonlinear filters, how might these continued innovations completely revolutionize fields we're only just beginning to explore? Think about hyper-precise medical diagnostics, analyzing signals from the body, or maybe entirely new ways to monitor subtle environmental changes using sophisticated signal filtering.
That's a really provocative thought. Where else will these powerful mathematical tools take us? What new signals will we be able to extract and understand? Thank you for joining us on this deep dive today. We really hope you feel incredibly well informed and maybe just a little inspired to listen a bit closer, look a bit closer at the hidden digital processing happening all around you.